Hello everyone, welcome to lecture 11 of the course on diffusion models. I am Dheeraj Madan and today we look at Poisson Flow Generative Models. So this is a paper by Zhu et al. I'll post a link to this paper in the description box below. So first of all, the idea of this paper is that as in many other generative models, the idea is to start from one simple distribution and transform it to the data distribution you want. Right? So start from a simple distribution and then you transform to your desired distribution. And this is the distribution of your data. So you will see this idea, for example, in normalizing flows. You will see the same idea in GANs, and now this paper also tries to do that. But note that in diffusions, the models which we have been looking at so far, they actually do not follow this protocol, because here this transformation, we are looking at a deterministic transformation. Okay, whereas in case of the models like diffusion, the transformation is itself a stochastic transformation. So just to give you, a high level idea of how this sort of transformation works is that essentially, let's say your points are in some n-dimensional space. Okay, what you do is that you append an extra dimension. Okay, so basically you transform every xi to xi comma 0. That will make it an n plus 1 dimensional point. And then you look at basically the extra dimension is what you can interpret as the z-axis. And then essentially you look at points on basically the base, on basically this base plane. Okay, so this z equals to 0 plane. So z is the last axis I have appended. So all these points lie in the n-dimensional plane in the n plus 1 dimensional space. And the idea is that how do I generate the distribution of these points? Well, I look at a hemispherical surface, a very large hemispherical surface, and I consider uniform distribution over this hemispherical surface. And now what I try to do is that I transform this uniform distribution to the distribution of my points. So what I'm going to do is that I'm going to transform uniform distribution to the distribution of my points, data points. Okay, so this sort of transformation is what we will achieve via our Poisson flow generative models. Okay, so essentially, just to give you an idea, so this transformation is based on the ideas of electrostatics. So for those of you who haven't looked at it for some time, so I'll just review the basics of electrostatics. So this is something which you all have studied in high school, or maybe in your first year of your undergrad, first or second year of undergrad. So mostly I think most of you would have studied in your high school. So let's review this particular background on electrostatics. Okay. So firstly, let's say we have 2 points, okay, q1 and q2, okay, which are separated some distance apart. Now what is the force between these 2 points? What is the force which the first point exerts on the second one? So that force is given by Coulomb's law, which is q1 q2 over 4 pi epsilon naught r square over r times r cap. So the direction is given by r cap, right? So the direction pointing from point 1 to point 2, that's the r cap direction, right? So this is the force which it exerts. One way to interpret is that q1 creates a field, creates an electric field E, and q2 experiences this electric field. Okay, now how do we now understand this? So let's say yeah so let us say that, you know, when you have a point charge q, it creates a sort of a field around it. So the field at any point, let's say that q1 is located at a point x, then at any point y, the electric field is given by q1 upon 4 pi epsilon naught y square. Okay, so it's y minus x square. Okay, it's then squared norm times y minus x cap. Okay, so that the direction from x to y, right? So I can actually, okay, y minus x cap looks a bit odd. I'll just write y minus x over norm of y minus x cubed. Right, because y minus x cap is y minus x over norm y minus x. Okay, so this is the electric field which it creates at a point y. Now the force experienced by any charge which is located at that point is given by q2 times the electric field at that point. Right, so this is how you interpret it in the language of fields. Okay, now again this is for 3 dimensions. But you can also sort of generalize this to n dimensions. So we'll just come to that. So this is essentially the field created due to a single charge. Now what happens if there are multiple charges? So let us say for m charges located at points x1 up to xm, okay, the electric field at a point y is given by 1 over 4 pi epsilon naught summed over I from 1 to m qi times y minus xi, okay, over norm of y minus xi cubed. Okay, cubed because I have to do a square in the denominator, but then I also need to add the direction. So to get the direction vector, I do y minus xi over norm y minus xi, and that puts a cube in the denominator. Okay, so this is for m charges. And if you have, you know, multiple charges, then if you have a continuous distribution of charges, so this changes to an integral. Okay. So the electric field at any point y is now given by 1 over 4 pi epsilon naught times integral of rho x y minus x d cubed x over y minus x cubed. Okay. So rho x is the charge density. Okay. Now another idea which is slightly more difficult, but I think many of you might remember from high school, some of you may not, is this idea of Gauss law. So what is Gauss law? So Gauss law states that, let's say you have some closed surface. Okay. And let's say some closed surface S, and now you have some electric field. Okay, now let us say that this surface has some charges inside it, q1, q2, qm. Okay, then essentially if you take the surface integral of E dot dA over the surface S, what you will get is q enclosed over epsilon naught. So when I say integral E dot dA, what I'm going to do is that I'm going to divide the surface into small patches of size dA. Then I'm going to take the dot product of, you know, the electric field at that point times the area electric field at this point times the area, and I'm going to add it all up. And you know, in the limit of these patches going to size 0, I'm going to get integral of E dot dA. This essentially equals Q enclosed over epsilon naught. So Q enclosed is the total charge which lies within this surface. So Q enclosed is going to be sum over I Qi over epsilon naught. Right? It could be continuous charge also, in which case I might have to take an integral, but this is how it will look like. Okay. And yeah, so this is what is called as Gauss law. Now in n dimensions, so this was all for 3 dimensions. So in n dimensions, actually Gauss law will just carry forward. But you know, to look at the essentially, you know, the electric field at any point, what we'll have is that so basically so let's say you have some charge. Okay, so you have some charge at point X, and I'm looking at, you know, the electric field at point Y. So what is it going to be? So the electric field at point Y is given by, again, rho X, or in general, you know, okay, it's so let's say we don't have some single charge. Let's say we have some charge density and we are looking at some point Y. So the electric field at any point Y is given by integral of rho X times Y minus X over norm of Y minus X to the power of n minus 1 dnx, right? Okay, I think it should be to the power n, right? So for 3 dimensions you have to the power n in the denominator. For n dimensions you will get to the power n. For 3 dimensions you have 3, right? Because there is a y minus x also on the top. So this is how the electric field will look like, and then there is going to be a normalizing factor of epsilon naught and the surface area of a unit sphere in n dimensions, right? So a unit n minus 1 dimensional spherical surface in n dimensions, I'm going to take its surface area. That's what I'm going to call as Sn minus 1 1. So for 3 dimensions this is 4 pi. For n dimensions it's just going to be some Sn minus 1 1. So this is how, you know, the electric field looks like, and Gauss law also just carries over. Now why are we doing all these things? Okay, so the idea over here is as follows, that let's say you start with some distribution on the equator of a sphere, right? So this is a sort of like an n plus 1 dimensional space, and you have some points, you know, your data points which lie in the n dimensional equatorial region, right? So basically I just append a 0th axis, a z axis whose value is 0 onto, you know, points on the sphere, and you know, I let the points sort of evolve. And the way I'm going to evolve them is that, let's say that I evolve them under their original electric field. So let us consider evolution of points as so how do I let the points evolve? I let the points evolve as dx by dt equals electric field at x at time 0. So basically at initial time the points all lie on the equatorial region, and I compute the electric field, and then I let them evolve under the original electric field, right? So as the points moving, the electric field will also change, but I don't let that happen. I just, you know, let the points evolve under the original electric field at time 0. But you know, at basically, yeah, so as the points are moving, they'll reach different points in the space, and then the electric field is varying with space. But at time I just keep it equal to, you know, the original electric field. So now what's going to happen? What do you think? Like, let's say I evolve them until they hit the surface of a hemisphere. So you have some charge density here, it evolves and it hits the surface of a hemisphere. So what do you think is going to happen? Maybe you can try writing in the comment section below, what will be the sort of distribution of the points you will get at this surface. So the answer is that if points are evolved under this sort of equation, then essentially you will get a uniform distribution on surface. And why is that so? Why is that so? So let us consider, some region. Okay, let's say you have some points which lie on this surface. They are coming from some distribution which is, say, pxx. Now let's say that there is a small patch on this equatorial region, and this small patch, okay, each point evolves according to the electric field it is experiencing. And finally it hits the surface of the hemisphere. So when it hits the surface of the hemisphere, and like moving under the same electric field, so essentially it creates some patch of points over here. So we need to compare the density of points here as well as here, right? So let's just call this region dA, let's just call this region some d omega. Now what's the relation between the density here and the density here? So the idea is as follows. Okay, let's consider like if you are experienced with applying Gauss law, so let's consider a sort of a three-dimensional bounding box which starts just above the surface, and then it ends just before the curved region. So there is some sort of a bounding box over here. Now if you look at the now let's try to apply Gauss law over here. Okay, so if we apply Gauss law, then essentially the electric field along the walls of this space is parallel to the walls. So if I have to compute integral E dot dA, there will be some contribution from the walls. And that is just zero because along the walls the electric field is along the direction of dA. So this contribution is going to be zero. Now I'm going to get some contribution here and I'm going to get some contribution from here. Now at this point, at this region dA, the electric field just above the surface, right? So if you remember from electrostatics, so just above the charged surface, the electric field is going to be sigma over epsilon naught, where sigma is the charge density. So here the thing is that okay, I didn't probably tell you what the electric field is. So here what we are doing is that initially the points, they all lie on the equatorial region. So essentially what I'm going to assume is that each point is a unit charge. And now I let them evolve under this. Okay, each point is a unit charge. These charges create electric fields. So at time 0 I compute the electric field at every point, and then let the sort of points evolve under this differential equation. Now since originally the points, they came from some distribution px, so the charge density was nothing but px over epsilon naught. So charge density was nothing but pxx, the initial PDF, and over epsilon naught will tell me the electric field just above this patch. Once I know the electric field just above this patch, I can compute the sort of sort of flux at this point by px x over epsilon naught times dA. So the flux I usually computed pointing outwards. So basically this I'm going to write as minus dA. And at this region, what's the sort of electric field? So at this region, the electric field, okay, let's say in the limit of the radius of this hemisphere approaching infinity, so that all the points are concentrated within some small region as compared to R. So essentially the overall electric field at any point which is say quite far apart is going to be just the total charge which we have. So the total charge is 1 unit, because I am assuming this density is the PDF over okay, so this is the overall charge, and then as I told you, the Coulomb's law in n dimension, that's over Sn minus 1 times epsilon naught times essentially the quantity d omega, which is the area at this point. Okay, so from here what do I get is that dA by d omega is proportional to px. Okay, so essentially d omega by dA is proportional to pxx. Right, so essentially d omega is proportional to pxx dA. And now if you apply the law of the transformation of probabilities, so apply the law of transformation of probabilities, basically the change of variables result, and what you'll get it is that if the original distribution was px, then finally you have a uniform distribution over the surface. So this was how it's going to evolve now, but the goal was that I wanted to start from some simple distribution and get to the distribution of points. What I have done is that if I start from the distribution of points, I can get to a simple distribution. So how do we do the reverse process? Well, we can evolve them under the differential equation, which is precisely the opposite. Right, so essentially instead of starting from the equatorial region and moving towards the hemispherical surface, I start I start the points as uniformly distributed over the hemispherical surface, and I let them evolve under the opposite differential equation, which was dx by dt equals minus of ex. And as they hit the equatorial region, this is going to give me the distribution of points on that equatorial region. So this is going to be my algorithm. So compute electric field E of x as the electric field corresponding to particles placed at z equals to 0 in plane Rn plus 1. Right, so basically each particle is assumed as a unit charge. So placing points as xi tilde, right, which equals xi comma 0 in Rn plus 1 on z equals to 0 plane. Now we start from uniform distribution on upper hemisphere and evolve points as dx by dt equals to minus of ex until they hit z equals to 0, and this will give me the distribution of points. So basically essentially I'm going to start with uniform distribution over the surface of this hemisphere, and what I do is that I just sample a point uniformly distributed over here, and I let it evolve under the electric field, assuming that the electric field is coming from my the points distributed according to the training data on the equatorial region, and then I let it evolve, and that gives me a sample of the point from my distribution. Now initially, of course, the evolving this under this electric field might be computationally expensive. So what you do is that you learn a neural model which can estimate the electric field at any point given by the training data, and then once you have estimated that, you essentially allow you start from a point uniformly distributed over the hemispherical surface, let it evolve until it hits the equatorial plane, and essentially we are saying that will give you a sample of the point from the distribution defined by your data. Yeah, I think it's a very high level idea, so this is a sort of a difficult paper. I have tried to give some intuition for the same, some intuition for the how it works. So you can read further more details in the paper itself. So thanks a lot. Bye.